right, good afternoon, everyone. So in a week from today, we'll have the second midterm. It will cover up to and including Unit 8, not this Unit 9. You'll be able to bring in a note sheet with two sides, so you can put something on the back of your first note sheet if you like. Any other questions? Or any questions about that? Yeah.
It's just 5 to 8, not 4 or 3, nothing like that.
Yeah, I mean, the class is kind of built
Yeah,
on
sure.
itself, but I'll be focusing on 5 through 8.
Okay. Thank you.
Mm-hmm.
Yeah, be careful, do two single-sided as opposed to one double-sided.
Two single-sided is fine. Yeah.
Will you open like a practice midterm or anything like that?
Yeah, I will post a practice midterm, as well as some extra practice problems, just like the first midterm. All right, great. Anything else? Okay, so today we're going to talk about a whole bunch of different issues and tricks for training deep networks. So we'll begin with learning rate scheduling. So just to review, when we talked about convex optimization, we saw that in that case, you wanted a small learning rate. If your learning rate was small enough, you're guaranteed to converge to the local minima, or to the global minima for convex, or more generally, a local minima. The trouble with, and if you use a small learning rate, it takes you longer to converge, but the only price you really pay is waiting a bit longer. When you work with non-convex cost functions, or especially deep networks, the issue is that small learning rates can actually cause convergence to bad local minima. So sort of illustrated roughly in this picture. So this is the global minima we would like to converge to. You can see we have these other local minima here. So if I start over here and I slowly go downhill with small step sizes, I'll converge here, and I won't really leave that point. And that would be bad because my cost is not as low as it could be. So the idea then is that if we can use large learning rates, we can possibly jump over those local minima, which tend to be shallow. So, so the idea is we want to sort of like skip over these. Another approach is to use something called momentum. I think you saw momentum back in the lab for Unit 6. In momentum, you are converging, but you sort of have some momentum, and so it just keeps going in the direction it was traveling. So that's another way to possibly jump out of this local minima. And in practice, the sophisticated algorithms have all these different tricks all mixed together. So a typical thing, but there's sort of an issue. If you use a very large learning rate the entire time, you'll never settle in the bottom of this minima. You'll keep jumping around, because we're going to be using mini-batch stochastic gradient descent, and the gradient is never quite correct, so it will never settle. So that you will never really get to the bottom with a large learning rate either. So typically what you want to do is you want to schedule your learning rate, meaning at the beginning, use a large learning rate to try to escape those local minima, and towards the end, use a small learning rate to try to converge well into the global minima that hopefully you found. So first use large, then small. Now, this is just the prototypical scheme. There's actually many different variations on this. So, for example, this is an approach called the one-cycle learning rate. And this is, you see the iterations here, and this is the learning rate vertically. So we start at this pretty small value. And in this case, you actually increase the learning rate up to a maximum value. And then you decrease back to that same value, and finally you go down to a very small value for that final convergence. So I think the advantage of this versus just starting here is that in this warm-up phase, various things in the optimizer can get configured properly, because the optimizer has all sorts of things like adaptive step size, momentum, and stuff, and those mechanisms take some data to get working right. And so during this point, or during this phase, perhaps that happens. All this stuff is not super well understood. It's more of like an art than a science. But this learning rate schedule has been shown to work well. Another one is to do something like this over multiple cycles. So you could keep going up and down and up and down and up and down. And there again, you hope that at least in the final cycle you have converged in a good global minima. With these multiple cycles, or even this one cycle learning rate, the maximum and minimum values here are things that you need to tune. And so there's a way of doing that using what's called the learning rate range test, which is also just sort of a generic way to quickly figure out a good learning rate for your problem. So in the learning rate range test, learning rate range test, over one epoch, you start very small and you linearly, this is your learning rate, start very small and linearly increase your learning rate to something very large. And you just do this over one epoch because you want to do this quickly without really spending much time. It's just a way of figuring out, roughly speaking, what is a good place to start here and what is a good place to peak. And when you do so, you get a plot that looks something like this. So for these very small learning rates at the beginning, you're not really making much progress. And so if you plot the loss, it's just pretty close to where you started. All of a sudden, and notice that this is on a log scale, all of a sudden, things start to take effect and the loss decreases. It's not decreasing to a very low value, but that's not really important. You can see that the loss is changing quite a bit. But eventually you get to these really large learning rates that where things start to stop improving and then in fact go unstable. And there's various heuristics, you can read about them, various heuristics that will say like, okay, look at this value right when things started to change, look at the value right when things saturated, and use those two values as those two values there. There's several variations on this. Other people say, look at the place where the slope is maximized, and so on and so on. But what they have in common is just a rough way to scan over a large selection of learning rates to figure out for your problem, for your batch size, and so on, what are some reference values. So learning rate range test, one cycle. But all this stuff for a given problem, for a given architecture, for a given batch size, needs to be played with. Okay. And these learning rate schedules are implemented in PyTorch, so you tell it, I'm going to use this scheduler, and then the optimizer just reads the learning rate. Well, actually, there's a way to call the scheduler to tell you your current learning rate. So it's all very nicely automated. Okay, any questions on learning rate? Okay. Next is a trick called batch norm. So batch norm is a popular trick to speed up training, and it can also increase performance. The intuition behind batch norm comes from the intuition behind standardization, which we learned way back in Unit 4, I think. In standardization, what you do is you want to make all your features, let's say, zero mean and unit variance. And we saw that that way, it's not like you have some features overwhelming other features in terms of your regularizer. It could also help, perhaps, like if you know the size of all your features, then maybe the learning rate you need for your model is predictable, because the learning rate is going to depend on the size of the gradients, which are going to depend on the size of the features themselves, and so on. So we know it's generally a good thing to do some sort of standardization to your data going into your network. Well, what you do in batch normalization is you, in some sense, repeat that normalization at every single layer of your network. You re-normalize or re-standardize your data. And it's not only in every layer, it's actually, you do this separately in every channel. So at every channel, at every layer, you normalize. Now you go one step further. In addition to, let's say, standardizing mean zero variance 1, you then, on top of that, in case that there's some other value for the mean and variance that's better than 0 and 1, you actually learn a new value. Okay, so this is the approach. In terms of the equations, just to be explicit, here we have, and different people apply this at different places. Some people say you should apply this to your linear scores before your activations. Other people say, no, apply it to your activations. But here we're doing it with the linear scores. So these are the linear scores. This is the batch index I, channel index M, spatial indices J1 and J2. You can see we are doing an empirical mean, sample mean, over all the batches and all the pixels. Sorry, all the elements in our batch and all the pixels. So now we have something that is specific to the layer and the channel. So this is going to be our mean. Now that we have this mean, we can also compute a sample standard deviation. So we take our data, subtract the mean, square it, average it over the same things as before. We'll add a small epsilon that will prevent this thing from going too close to 0. And then finally, once we have the sample mean and this sample standard deviation, here's where we do our standardization. You can see why we don't want this to go too small to 0, because if this, for example, maybe when you initialize things, you get exactly 0 for this. Well, if that was 0, then you'd be divided by 0 and you'd have a problem. So this is in there. This is just a small number to keep this from getting too small. And here's the standardization step. So now we have separately standardized data in every layer and channel. Now we go one step further and we scale this with a learn parameter, and we have a learn shift. And so finally, here are the normalized quantities. Okay, so we do this in every channel, every layer separately. Any questions on the approach? All right, so let's see how well this works, or maybe why this works. Well, let's just see how it works. Let's focus on the bottom here. So this picture is from the original paper, and we start out with a network that is trained without batch norm, and it's this black dashed line. These blue diamonds are all at exactly the same level. This is accuracy here. It almost looks like the blue diamonds are at different heights, but they're there just to be a reference, to say these are all the same values of the accuracy. So we train this. This is the Inception network. We'll talk about it later today or maybe Monday. And we're training it here for 30 million iterations, 30 million batches, and getting up to this accuracy of 72% or whatever. That's without any batch norm. Then we add batch norm, changing nothing else, and we get the red dash line. And so you can see the convergence has been improved by more than a factor of 2. And it's even going a little bit higher in terms of accuracy, not very much. Next, what if we multiplied that learning rate by a factor of 5? Now we get way faster convergence. But the important thing is that if we would have taken the original network without batch norm and multiplied its learning rate by 5, it probably would have gone unstable. This is something that we can only do because we put in batch norm. We can even go further. We can increase the learning rate relative to the original one by a factor of 30. When we do that, we get fast convergence, but we actually get a boost in accuracy as well. Okay, so this is showing all the advantages of batch norm. Now, just as sort of a little experiment to see what happens, we're actually going to use the times 5 step size approach, replacing all the ReLUs with sigmoids. So usually this won't work at all because of the vanishing gradient problem. We know that ReLUs are needed for deep networks, sigmoids cause the gradients to vanish. Well, it turns out when you use batch norm, you actually get some robustness against that, and you can use a sigmoid. It doesn't work as well as a ReLU, but the fact that it even gets close to 70% accuracy is pretty remarkable. Okay, so that's what this experiment showed. Okay, any questions on these results here? Is it making sense? Okay, so it's really speeding up training as well as improving the accuracy. The original paper had kind of a strange explanation that didn't really seem to, be very well explained or defined. It was something about covariate shift, reducing covariate shift. So after that, a lot of people wrote other papers that analyzed batch norm, gave different explanations of why it worked. So clearly, one thing that it's doing is it's reducing variation across channels, across mini batches, making everything much more predictable, much more consistent. As a result of that, it helps to decouple layers, meaning without batch norm, if you make a change in one layer of the network, you will see the effects of it many layers down in terms of their behavior. With batch norm, it helps to decouple these layers because if you make a big change in one layer, because you're normalizing the next layer, standardizing it, it's much less impacted by that change. So it helps to decouple layers. People have shown that actually, if you analyze the cost function that you get after you stick in batch norm, that cost is smoother. So there's all these different explanations of why it works, but it really does work quite well. Okay, so that's batch norm. Any questions on batch norm? Okay. All right, another approach is called dropout. So dropout is used to reduce overfitting. If you use it well, it can have a great effect. If you use it incorrectly, it won't work for you. And I notice in the projects a lot of students are using it incorrectly and they're not really seeing the effect. So let me try to explain what's happening and how to use it effectively. Okay, so the main idea behind dropout is a little bit counterintuitive. The idea is that during training, you actually remove a large fraction of the nodes from your network. And the way you remove them is you just multiply them by 0. So some people draw these figures like this. Maybe this is your neural network. Data is going that way. So if I multiply a bunch of these nodes by 0, then essentially it's like I'm taking them out of the network, and now you can see there's many fewer connections in this network. So you actually remove a different random subset of neurons every mini batch. So the subset you remove is constantly changing very quickly. You do this at training, but you don't do this at test time, at inference time. At inference time, you use the full network. So there's different ways to understand, how and why this is working. From a very crude perspective, you could say, well, it's like in some sports, when you train, you do all these things that make your life a lot more difficult than when you race or when you compete. So like when I was a swimmer in high school, and we used to wear like 8 suits on top of each other to increase the drag during training. And then during race day, we would wear like one suit, a lot less drag. So this is sort of similar. It's like you're making training really difficult, really making the network work during training, but then during testing, it has a much easier time. That's a very crude explanation. Another way to understand it is based on something that we'll actually get to in the next unit, which is what are called ensembles. An ensemble of predictors is like a family of predictors that are each kind of weak, but when you use them all together, they get really strong. And so it's sort of like you can imagine every time you remove a subset of nodes, you get this relatively weak neural network that remains. But then if at test time you include all the nodes, it's sort of like in parallel, you have a whole bunch of these guys working together. And so you have all these weak networks, and they were trained to work well individually. And so in the end, but in a random way, and in the end, they do well together. Okay, so we'll talk more about ensembles in the network, but in the next unit, but that's sort of what happens. Okay, so the specific way you do this, like I mentioned, is each of your activations. This is in layer L. Oh, and by the way, I should emphasize, this is typically done before dense layers only. You don't want to do this in the nodes before convolutional layers because those nodes act kind of differently. So this is just for dense layers. So for dense layers, we know we have activations that only have, for layer L, there's only 2 parameters. There is the batch index and the index along the vector of features, because we just have a vector of features with dense layers. So what you do is you multiply those by a random variable. We'll call it D. Separately for every layer, batch index and channel index. That random variable is Bernoulli, so it's either 0 or non-zero. The probability that it is non-zero is called P. That probability is something you need to tune. A default value might be like 0.5, meaning 50% of the chance, 50% of the time, any given node is taken out. Okay, now, so when you decide on your value for P, you actually use 1 over P as the value that you multiply the activation by when it's non-zero. Okay, so if you use P equals 0.5, that means when the activation is on, it's actually multiplied by 2. When it's off, it's multiplied by 0. The reason for using 1 over P here to match this P here is that on average, the activation has a value of 1, right? Or is being multiplied by 1. So if this P goes to 0.1, it's only on for 10% of the time, then this value is going to be 10. So when it's on, it's very strong, and when it's off, it's 0. On average, it has a value of 1. So that's the idea. And then this is only done during training. Full network is used during testing. So is the recipe kind of clear? Okay, so this behaves a little bit counterintuitively, especially during training. So during training, when you turn dropout on, you'll notice the performance gets a lot worse. And this is because when training, you're using these much weaker networks. So the training takes longer, the training performance is worse, but that's expected. It's only when you go into the inference mode, when you use the full network, that you really see the gains of this. Okay, the other thing is that because you're reducing the complexity or the capacity of your network, if you have optimized your network so that it's working really well, it has just the right number of hidden nodes and everything, and then you put in dropout, it's probably not going to help, because dropout wants a network to be too complicated. It's sort of reducing the complexity, so it's trying to prevent overfitting, you could say. So if your network is not overfitting and you use dropout, it's probably not going to help. So generally speaking, you want to have an overly wide network, and then dropout works well. So it's like if I, maybe double the number of nodes and then randomly use every other one. On average, my network has the capacity I want. It's just that now I have a whole bunch of extra nodes that I can swap in and out during test time. Okay. So what I see in the final projects is students will optimize their network, and then at the end, they'll see if dropout helps. Usually it doesn't, because their network has been optimized to work well without dropout. So then dropout doesn't work that well. Okay. So that's the thing. May need to increase the number of channels to see the beneficial effects. All right, any questions? Okay, and again, don't generally want to use this on the inputs to convolutional layers. There are versions that are supposed to work well with convolutional layers, but they're not really universally accepted. You can find some, but I think most people just use these for the dense layers. You also don't want to apply this to your final outputs. Those final outputs are all very useful. You don't want to drop them out. And if you have an all-dense network, you would not want to apply this to your inputs, because your inputs are all very useful. It's just the hidden nodes that you're dropping out. Okay, so that's dropout. Any questions on dropout? Okay. All right, another trick is data augmentation. So the idea here is our training data sets are usually smaller than we'd like. We wish we had more data. So depending on the application, the nature of your training data, you can sometimes do tricks that appear to make it larger than it is just by working with the data you have. So with images, for example, you could do things like flipping them, shifting them, scaling them, rotating them, cropping them. So for example, if this is the original image that we have, we can make it look like a new image just by zooming and cropping this portion. It looks like this. Or we zoom and crop differently, and it looks like this. And now it looks like we have 3 different images where actually we just started with 1. Of course, you can also do a left-right flip. In most cases, that makes sense. You have to be careful with up-down flips, because a lot of our images, there is a proper up and down. So like if you're working with images that have outdoor, there's sky above, grass below. If you flip it up down, it just looks quite a bit different, and it actually could hurt. It could confuse your network. So usually left-right flips are okay. But in some cases, it's okay. You can do rotations, you can do up-down flips and so on. It just depends on the data you have. Another common one is what's called color jitter. So like you you mess with the colors. So, if you said, well, this image would be just as valid if I had, yellow here and blue here, well, then you can play with the colors and get like many different versions of this image with random colors. In PyTorch, all this augmentation stuff happens in the data loader. You just give it a list of augmentations, and then it does this as it loads the data from disk or memory. It just does the augmentation and gives it to the GPU. There's a nice PyTorch tutorial here about how to do that. All right. Okay, so that's data augmentation. Any questions on that? All right, so here's here's another one. ReLU activation. So we saw before, ReLU are useful to prevent vanishing gradients. But now this causes a new problem, which is it's not a super common problem, but it is something that can happen, which is the dead ReLU problem, where a subset of nodes can get stuck outputting 0 for all training and all test samples. So it's like there's these nodes that somehow, when training, you got into this local optima that is just basically not using this node at all. So it's getting kind of wasted. As a way to prevent that, a simple trick is instead of using a 0 slope on the negative side of the ReLU, you make it a very small positive slope, like 0.01, I think is a default value. So this is called leaky ReLU. And now you do have a little bit of a gradient on that left side, and then that prevents those nodes from getting stuck. You can go even farther and say, why don't I learn that left slope? So instead of fixing it at 0.01, make that a learnable parameter. So that's all directly implemented in PyTorch. You don't have to worry about deriving anything. So these are all different things that definitely can make a difference in practice. Any questions there? All right. And then more recently, people have played with smooth versions of the ReLU. This one is called the exponential linear unit. So when you look at the side to the right of 0, this is exactly the same ReLU. So instead of the left side being flat or sloped down with a sharp edge, this one is a smooth function. So that smoothness can help with optimization. But also it's designed with a very specific shape here, such that if you start with data that is Gaussian, I think with mean 0, variance 1. So if with a ReLU, I started with Gaussian data, mean 0, variance 1, and I look at the output of the ReLU, now it's going to have a positive mean, right? Because all the negative stuff got set to 0, and the positive stuff remained. Well, they figured out a shape here such that when you put in that same Gaussian, and I think even, I don't remember exactly, I think it's several different distributions. When you put it through here, this is shaped so that the outputs are still 0 mean. So that can help your network learn a little bit better. So in some cases, they show experiments where this has a huge benefit. In other cases, people try it and say, didn't really help me. But these are all things you can try in the project. Okay, so those are activation improvements for the hidden layers. Any questions? Okay. All right, so let's do a little demo. So in this demo, we will make a simple neural network. It's basically 2 dense layers, 2 conv layers followed by 2 dense layers. The conv layers use ReLU and max pooling, followed by 2 dense layers at, and there's CIFAR 10 as a data set, so there's 10 classes. So the inputs are 32 by 32, and the outputs want 10 final outputs because we have 10 classes. So in this case, we're going to use the standard cross entropy loss. I don't remember exactly how many hidden nodes we used and all that, but if we look at the curves, this is training, this is validation. And so what you notice during training, let's start with the baseline network. The blue one, we see that the training accuracy gets close to 100%, very close to 100%, maybe even 100%. However, and this is epochs, over 100 epochs here. However, when you look at the validation accuracy, this is settling at maybe like 67%. That's the typical thing you see with these deep networks is really great training accuracy. Validation accuracy or test accuracy is not nearly as good. So, okay, how do we improve this? Well, what if we add batch norm? So when we add batch norm, not too much happens with training, still getting like close to 100%. But now, validation, get a big boost. We're up to maybe like a 5% improvement. Next, on top of batch norm, we can add dropout. When we do this, you look at the training, looks like things got a lot worse. The training is now, getting to like 80%. And it's taking longer to get up there. Here it's converging pretty quickly. Here it's taking a long time. So it looks like things are not going that well, but when you look at validation, actually, this is a huge boost over what we had before. So we're really seeing the benefits of dropout here in validation, but not in training. The final thing we did is we added augmentations. For whatever reason, the augmentations are not helping. Not exactly sure why. Here we have the training accuracy is a little bit worse. Validation accuracy is almost as good, just a tiny bit worse. So maybe with some other tweaks, we could get it to work better. Maybe better step size or choosing the number of channels better and so on and so on. So it's just an example of what you can find and the sort of things you can do in your final project. Try different options. Okay. Any questions on that demo? Okay, so you can obviously see all the code there. All right, so moving on to the next topic, which is transfer learning. And the idea behind transfer learning is that these networks, like, for example, AlexNet is one we've talked about. This, like, you wouldn't be able to do this on your own laptop to train it. It would take too long. Generally speaking, these things, they have many millions of parameters, take like weeks on clusters of GPUs to train. So this is not something you want to try to do at home. However, usually what you learn in these networks is actually much more universal than you might think. So especially these vision networks, what you learn in the early layers works well for a very broad range of images. So it's not just ImageNet. If you have collected your own data, maybe you're working on crop science and you want to build a detector for weeds versus crops, for example. All the stuff you learned on ImageNet data in the early networks, early layers, that's fine. You can just keep all that. In fact, the only thing you really need to change are those final dense layers, maybe even just the last dense layer alone. So you don't have to retrain this network from scratch. You can freeze almost all the layers and just train the very end to match your task. And that's definitely doable. That's easily done on a laptop. So that's the idea behind transfer learning, is you adapt this pre-trained network to a new task. The early convolutional layers, they're universal, you just keep them fixed. You retrain the later dense layers. Maybe all of them, maybe just the last one. Depends how much compute you have, how much training data you have, all that stuff. So, and there's other ways that people use this too, like one thing that we see in my research group is we work on a lot of regression tasks for images where we're trying to, clean up images, deblur them, and so on. And so a natural question is, what is a good quality metric for images? If you give me two images and you want a metric that says how good this approximation looks, there's traditional things like mean squared error end up not really correlating that well with what someone would say about how good they look. Some intuition behind that is if I have like a target image and I give you a perfect copy of that target image, but I shift it by a few pixels, and I compute the mean squared error, it's going to be terrible because they're not aligned. But visually, the approximation is perfect. Like your eye can't tell that there's a few pixel shift. So that's just an example where what you see with your eyes doesn't really correlate with what you see with the mean squared error metric. And this happens for other metrics as well. So people have worked on these perceptual quality metrics, and they almost always start with putting the image through a pre-trained network like AlexNet, and then getting the features in one of those early convolutional layers, and just saying that represents my image. Those things are much more closely aligned with what the brain works with. And then they'll put the true image through that, they'll put the approximated image through that, and then they'll compare, maybe they'll look at mean squared error in that feature space. And that works really well. So that's another way you can use these pre-trained networks. Okay, so the other nice thing is in PyTorch, the Torch Vision models package actually gives you all the weights for these famous pre-trained networks. So you can download AlexNet, you can download all the weights, you can use it, you can retrain the last few layers on your training images, you can do all that. So, and it's not just AlexNet, as we know, AlexNet was like the first deep network revision that really made a splash, but things got a lot better since AlexNet. And so in PyTorch's Torch Vision models package, you have a lot of these other really famous deep networks that came in the years after AlexNet. And so what we'll do in the next few slides is we'll go through these different networks, in the order in which they appeared to understand how the networks were changing, what tricks were being learned, what are additional tricks that make networks better, not so much training tricks, but more like structural, architectural tricks. So that's what we'll talk about next. Any questions on transfer learning? Okay. So we'll start with VGG. VGG won some of the contests in that ILS VRC competition in 2014. Remember that in 2012 is when AlexNet won them. So, okay, the question then is, well, what did they figure out? What did they change to go from AlexNet to VGG? So the main thing is that VGG, relative to AlexNet, uses smaller kernels, like 3x3 only, but more layers. Some of the intuition behind that is the following. So if I have an image and let me write it this way. I convolve that image with a kernel. I'll call it kernel 1. And I convolve that image, that result, with another kernel. I'll call it kernel 2. Well, if you remember your 3050, maybe even earlier class, this is equivalent to convolving the kernels and with that new kernel convolving the image, right? So there's this, what is this? The associative property of convolution. It actually happens for any linear system, and convolution is a linear system. So the idea is that in a deep network, as we know, we don't have just convolution going on. There's another very important thing, which is the nonlinear activations. But if for the moment, if we just sort of forget about those nonlinear activations and just think about convolution, if I go through 2 layers with a kernel, let's say this is a 3x3 and another 3x3, we know that that's equivalent to convolving that image with a convolution of those 3x3s. And what do we get here? What is the size of this convolved kernel if I take a 3x3 and convolve it with a 3x3? So who knows that? You kind of maybe graphically visualize it. So this convolution would be the full mode. It wouldn't be like any of those other padding modes. This shouldn't be too hard. It should be like basic 3050 for sure, 5200, maybe even 2050 stuff. Nobody knows? Yeah. 5x5, exactly. You can see this in one dimension. It's easier for me to draw. If I take a kernel of width 3 and another kernel of width 3, how many places can I shift this while still touching this? So I could start there. That would give me the first pixel of the convolved kernel. Then I move this to the right. It gives me the second one. Then I move it to the right one more, the third, then the fourth, and finally the fifth. And if I move it any further, they're not touching and I have 0 output. So essentially what happens is every time I convolve another 3x3, the effective width of the kernel grows by 2. So if I do this for 5 layers, I get expansion of 2 5 times. Actually, 4 times, because I start with 1 and I do 4 more layers. And then I will have, essentially it's like this. So you have K is the kernel size. If the number of layers is L, you get L times K minus 1 plus 1 is going to be the size of the width of the new kernel. So with a 3x3, I have 5 layers, I have 11, basically. This is called the receptive field. When you look at the cumulative effects of many small kernels, they add up to effectively a bigger kernel. So another way to say it is after 5 layers, if you look at 1 pixel of that image, it can take in information from 11 different pixels of the original image because of this receptive field. Okay, so if we're talking just about receptive field, what we've learned here is that one 11 by 11 kernel is sort of equivalent to 5 3x3 kernels in terms of growing that receptive field. But now, as we know, in these deep networks, they're not just doing convolution, convolution, and convolution, because if all we were doing is convolution, there's no point in splitting this up into 5 kernels. We could have just done it once with a bigger kernel. What's happening in a deep network is between every one of those little 3x3 convolutions is you have a nonlinearity that adds a lot of sophisticated actions to your neural network. And so when you put in those nonlinearities, those 5 layers, 5 linear, nonlinear layers is much more powerful than one 11 by 11 convolution with one nonlinear layer. Does that make sense? So that's what they figured out, basically. That it's better to use really small kernels and many layers versus bigger kernels and fewer layers. So here's kind of a picture. Again, this shows you more or less the shapes of what we call the feature maps as you go through the network. So we start with these ImageNet size color images. Then we go through two convolution plus ReLU layers before we do any max pooling. Finally, we reduce size by 1/2 with 1 layer of max pooling. So we go from 224 by 224 to 112 by 112. 2 more convolution plus ReLU layers, another max pooling, 3 convolution plus ReLU, another max pooling, 3 more convolution plus ReLU, max pooling, 3 more, max pooling, and then eventually flattening. Flatten this down, we have 3 dense layers. And these are just fully connected and ReLU. At the end, we finally get 1,000 softmaxes, which is what we need for ImageNet classification. So that's essentially the network. You can see it's not that different from AlexNet. It's mainly like they tweaked the number of layers, the number of kernels, where to put the max pooling. There may have been some other little things they did too, but this is like the big architectural change. And the result of this, so you do have more parameters in this network than in AlexNet, but it definitely worked better. AlexNet got 15.3% top 5 error, meaning that among the top 5 most likely or largest softmax outputs, that was the correct class. Whereas VGG 16, the 16-layer version of this, got 7.5, so about half. They actually had various versions, various depths of this from 11 to 19. And these lower layers are still respected. They're still used for other vision tasks. People don't really use AlexNet, but they do use this. However, so the cost of these extra layers and so on is 3 times the number of parameters in AlexNet. So it's definitely kind of an issue. Any questions? All right, I think we have time for one more. Okay, so when you look from 2012 to 2014, from AlexNet to VGG, there was some stuff in the middle year, 2013, but overall the trend is the networks are getting deeper, but the number of parameters was increasing. So 60 million for AlexNet to 180 million for VGG 16. So 180 million parameters, especially 10 years ago, was a lot of parameters. And they saw the trend, like we want to make things deeper, but they said we can't just keep increasing the number of parameters. We can't keep up. So there was, they said at Google, let's make a network that's really deep but much more efficient than AlexNet and VGG 16. And at the time, there was this film Inception that had this meme, we need to go deeper. And so they named their network the Inception network. It was also called the GoogleNet, but it became the first Inception network of several versions of Inception. And what was amazing about this is instead of 60 or 180 million, it used only 5 million parameters, but it got 6.7%, which is slightly better than VGG 16. So they're able to massively make a much more lightweight network, but still as powerful, if not more powerful than VGG 16. So one of the big tricks in doing so that they use here are what are called inception modules. The idea behind an inception module is it's like several convolution layers in parallel but with different kernel sizes. So it's sort of like this. So imagine that this is the feature map of the previous layer. So we have number of vertical pixels, horizontal pixels, and channels. And what we'll do is we'll use several convolutions in parallel. So we'll do a 1-by-1 convolution, and we'll stack the results of that into these channels of the output. We'll also do a 3-by-3 convolution, stack those here. We'll also do a 5-by-5 convolution and stack those here. And then we'll do a 3-by-3 with max pooling and stack those here. And so as a result, this gives us more flexibility. For bigger kernels, we can use fewer channels. We want to use fewer output channels because the total number of coefficients that we need to learn is a function of the kernel size as well as the number of outputs we have. So for bigger kernels, we want to use fewer output channels to keep the memory down. But for smaller kernels like 1-by-1, we can use lots of output channels. Also, these multi-size kernels can help with scale and variance. We can have big kernels, small kernels, and so on. So this was one of several tricks in there, but that's how they got this really good performance with relatively few parameters. Okay. So there's a few more ideas to cover. ResNets we'll talk about next, but this is a good time to stop. Any questions on anything so far? Great. See you guys on Monday.